Okay, now that we've kind of learned conceptually what limits are, let's learn how to evaluate them. You can evaluate very simple limits like this. What's that limit? Well, let's see. As x approaches 3, this is going to get closer and closer to 3. So this will get close to 6. When you add 5 to it, it'll get close to 11. So no problem with something like that. That's just a line which has slope 2. And as you approach 3, the value of the function approaches 11. So that you can do it, but it's no special reason to, okay? The value of the function at 3 is 11 and you're fine. Where limits are more important is, if you recall from when we first introduced them, they're important in situations like this, where, what did we have? I think we had x squared minus 9 over x minus 3 as x approached 3. And we notice there, as x approaches 3, the top goes to 0 and the bottom goes to 0. And so we had no idea what was happening because 0 over 0 is meaningless. And so what we did was we said, okay, let's take the limit and we'll break this up into x plus 3 times x minus 3 divided by x minus 3. And then as x gets closer and closer to 3, this number will always be the same as this. So they will divide out for anything other than 3. This just divides out to 1. And so now as x approaches 3, this approaches 6. Okay? So this is a more typical situation where you need to evaluate limits and want to find the information that limits give you. So this was a situation like this, if you recall, where the function looked like this, and as x approaches 3, the value of the function approaches 6. So it's in situations like this where you have 0 over 0 or anything over 0 where limits become important in giving you some information about a function. So let's look at some very kind of standard cases of 0 over 0 just to show you what can happen. Let's look at all of these cases. F of x equal x over x. We'll just take them one at a time. So x over x, what does that function look like? First of all, notice if I ask the limit, what happens as x approaches 0, both the top and the bottom are approaching 0, and they both, if you stick in 0, you get 0 over 0, which is meaningless. So if you stick in 0, you get 0 over 0, which is meaningless. But if you were to graph this function, what would the function look like? For anything other than 0, this number is exactly the same as that, so the ratio is always equal to 1. So the ratio would always be 1, and it's only at 0 that it's undefined, but now once we have the graph there, we can see the answer. As x gets closer and closer to 0, the value of the function approaches, actually always is, 1. So there the answer is 1, which you can do algebraically just by dividing that out, and you get a 1 there. So that's what the limit is. So the limit of that is 1. What if you have 5x over x? How does that change things? Okay, well, now, except when x is 0, that ratio of the top to the bottom is always equal to 5. So except at 0, the value of the function is always 5. So as x gets closer and closer and closer to 0, the value of the function is always 5. And so we say then that the limit is 5. Okay? So I do that just to show you that you can have anything of the form 0 over 0. Both this goes to 0 and this goes to 0. But we could have the limit be 5 or negative 5 or 15 or 123, whatever you wanted. All of those are possibilities whenever you have something of the form 0 over 0. Okay, let's try this one. Might as well just stick it in there as the function. Okay, what does that function look like if you were to graph it? Well, let's just throw in some points again. 0 over 0, it's undefined at 0. But if you put in any positive number, then this value will be exactly the same as this. And so the ratio will be 1. And if you put in any negative number, then the top will be positive and the bottom will be negative, but the ratio will still be 1. It'll just be -1, since this will be the negative of this, if x is a negative number. So the function looks something like that. So that's what the function looks like. And now if you remember from what we did in the last lesson, we look at that and we say, well, what happens as x approaches 0? Well, the limit from the left is equal to -1. The limit from the right is equal to 1, but the limit itself doesn't exist because there's no unique value that this thing gets close to, so say DE therefore does not exist. Okay? Not exist. Okay, very good. So that's that one. How about this one? Here you don't have a 0 in the numerator, but you do have one in the denominator. And if you recall, we graphed this function back earlier in an earlier lesson. And I mentioned to you this is a very important function. 1 over x, what does that look like? We spent time on it then, so I'm not going to spend time on it now. I'm just going to remind you what it looks like. It looks something like this. Okay, it looks like that as x gets very, very small. 1 over a small number is a very large number. It's an odd function. You put in a negative number, you get a negative number out. So you look at this and you say, well, what happens to this limit as x goes to 0? Again, if you think about the last lesson, we already talked about a situation like this. Here we would say there is no limit, doesn't exist. Doesn't exist. But if we wanted to say what happens to the limit of 1 over x as x approaches 0 just from the right, then the best answer would be, oh, it doesn't exist because it's getting arbitrarily large, so we'd say it's going off to infinity. And similarly, if you let x approach 0 from the left-hand side, then the limit doesn't exist. Why? Because it's going off to arbitrarily large negative numbers, so then the answer would be a negative infinity. So there's the answer for that one. Okay? What if we change this to 1 over x squared? How does that change things? Well, recall what the function looks like. Function looks like that. It blows up on both sides. And so here we'd say, oh, as x approaches 0, from both sides, the value of the function is becoming arbitrarily large, so it's going off to infinity. Would be the best answer. If you had a negative 1 over x squared there, then of course the function would be just the negative of that one. It would look like this instead. And there it would be going off to minus infinity. So those are all options. Okay? Finally, what if you have x over x squared? What does that look like? Well, x over x squared, they both are going to, both the top and the bottom go to 0, and it really doesn't matter. You got 2 x's here and 1 x there, and so if you divide out an x, from both the top and the bottom, you end up with just 1 over x, and there's going to be no difference between those two functions. They're going to look exactly the same because the domain of this one is the same as the domain of this one. Neither one of them allow x in part of the domain, and for anything other than x, this value is exactly the same as this. So this would look like that, and again we'd have the same answers before. This limit doesn't exist, but if you come in from the right, it's going to be infinity. If you come in from the left, it's going to be minus infinity. And similarly, if you made this an x cubed, then again, this graph is going to look exactly like that one, because again, 0 isn't in the domain of either of them, and for anything other than 0, that's exactly the same as that. So there you have, whoops, there you have infinity as your answer. Okay, so those simple little problems there really contain most all the various kinds of behaviors of functions when you get this 0 over 0. And so once you understand those, then you can just apply it to things that are a little more interesting. So for example, here's one right here. Okay, let's evaluate this limit at several different places. Okay, I'm going to abuse the notation here just to save some time and space. So first of all, as x goes to 0, well, let's see. If we were just to throw in a 0 both on the top and the bottom, what happens? I'm going to get 0 minus 0 plus 2, 0 minus 0 plus 6. Well, that's easy enough. There's no problems at all. That's just 2 over 6, which is the same as 1/3. So no problem at all at 0. What happens at 1? Well, at 1, we're going to get 1 minus 3 plus 2. That's going to be 0. And on the bottom, we're going to get 1 minus 5 is going to be negative 4 plus 6 is 2. Well, that's easy. There's no problem. No problem at all with 0 being in the numerator. 0 in the numerator, 0 over 2 is equal to 0. So that is just 0. So no problem at all there. Okay, so those two are fine. Now what happens as x goes to 2? As x approaches 2, let's see, you're going to get 4 minus 6, which is negative 2, plus 2 is 0. That's no problem. We'll have a 0 on top. But notice, we're also going to get 4 minus 10 is negative 6, plus 6 is 0 on the bottom. So now we have a case of 0 over 0. And as we just saw, when you have 0 over 0, anything was possible. What did we get for answers? 5, 1, infinity, minus infinity. No limit, or it doesn't exist. We had all sorts of possibilities of possible answers when you had a 0 over 0 situation. So you can't just claim what the answer is, you have to play with it. And the way to play with this one is to factor both the numerator and the denominator. So now let me go ahead and write this out. If we factor the numerator, it's going to be x minus 2 times x minus 1. And on the bottom, we're going to get x minus 2 times x minus 3. It factors. So now we can do the same sort of thing we did in the previous problem. We can say, okay, as x approaches 2, this value is always going to be exactly the same as this. And so for anything other than 2, this value is the same as this, so the ratio is 1, so you can just ignore them. And when x is equal to 2, then of course we got a hole in the graph. The thing isn't defined. But other than that, anything other than at 2, the function is going to look just like this one, just like that one. And so I don't even have to graph the whole function. All I have to do is to say, oh, well, as x approaches 2, I'm going to get 2 minus 1 is 2 up on top. Or I'm sorry, 2 minus 1 is 1 up on top. And what? 2 minus 3 is a negative 1 on the bottom. And so the answer is negative 1. So you just do the algebra, you can factor, you can cancel them out, and get the answer. And the reason is because this number is always going to be the same as that, so the ratio is 1, and you can get rid of it. So, so you have that. Let's do the last one. What happens as x approaches 3? I think I had. Okay, we can factor it again. First of all, if you put in a 3 in here, you're going to get 9. Minus 15 is negative 6 plus 6 is 0. So you're going to get 0 there. And here, if you put in a 3 rather, you're going to get 9 minus 9 is 0 plus 2. So you're going to get a 2 on top and a 0 on the bottom. As long as you have a 0 on the bottom, you've got to do some extra work on it. So let's go ahead and factor it again. Okay, so let's think about it. First of all, as you approach 3, this number is always going to be exactly the same as this, so the ratio is always 1. So you might as well just cancel those out because they're just going to cancel each other out to 1 anyway. So now let's think what happens as x approaches 3. And let's do it in 2 different pieces here. Let's first approach 3 from the right-hand side. Okay, as you approach 3 from the right-hand side, this is going to approach 3. This is 1, so 3 minus 1 is 2. The top is going to approach 2. And the bottom, this is approaching 3 from the right. So it's always a number just a little bit bigger than 3. When I subtract 3 from it, it's going to be a number very close to 0, but always just a little bit bigger than 0. It's going to be a positive number. So I'll put this in parentheses just to indicate that's what these 2 things are heading towards. This is heading towards 2 and this is heading towards 0. So now we go back to what we learned again earlier, that if you divide by a smaller and smaller number, the ratio becomes very, very big. This is positive and this is positive, so you're going to be going off to infinity. Okay? On the other hand, if you take the limit of this same thing as x approaches 3 from the left, then how do things change? Those cancel again. The top is still approaching 2 because this is approaching 3. When you subtract 1, it's going to approach 2. 2 is a positive number. Doesn't matter. It doesn't matter whether it's a little bit bigger than 2 or a little bit less than 2. The point is it's very, very close to 2. The bottom, on the other hand, is getting close to 0. And there it does matter which side of 0 you're on. Here's 2 right here. If you're at 2, if you're a little bit here, if you're a little bit there, you're still close to 2, and it doesn't affect your final answer at all. On the other hand, 0, if you're on this side of 0, you're a negative number. If you're on this side of 0, you're a positive number. So you have to be more careful. As x approaches 3 from the left, meaning a little bit less than 3, this is a number a little bit less than 3, you subtract 3 from it, this is going to be a number a little bit less than 0. So I like to put a 0 there with a negative just to indicate that it's a small, very, very, very small negative number. And what happens when you divide by a very, very small negative number? Again, it goes off to infinity. But here you have a positive, there you have a negative, and so now the ratio is negative. So that's the idea. Okay? Let's try just one more, just to show you some of the interesting things that you can have by way of limits. Although we've kind of hit the main ideas here. We're going to do trigonometric things next time. Let's try this. Okay, what happens to that as x goes to 0? Well, let's see. If we just stick 0 in, we're going to get square root of 100, which is 10. 10 minus 10 is 0 up on top. And you're going to get a 0 down here on the bottom. So 0 over 0. Again, we have no idea what the answer is going to be. It could be anything. So we have to do something clever. The reason I included this example is because the clever thing you do here is kind of a nice, clever trick in mathematics. What you do is you multiply by the conjugate. Let me show you what I mean. The conjugate. If you have a square root like this, then notice you have a negative here. You multiply both the top and the bottom by the same thing. As long as if whatever I have, if I have a over b and I multiply by a fancy form of 1, I haven't changed it at all. If I want to multiply it by 5 over 5, no problem. That's just a form of 1, so I haven't changed it at all. This is a fancy form of 1. It's this thing divided by itself, so I haven't changed the function. But this is going to be convenient because watch what happens now. When I FOIL this out, remember what it means to FOIL? You go first, multiply that by that, and the square roots go away. And I'm just going to be getting x squared plus 100. Then, just to save time and space, I'm gonna not write this part down. But now what do? Outer, inner, last. Outer is this times this. Notice it's 10 times the radical. Inner is going to be negative 10 times the radical. So those two are going to cancel out. And that's the reason why multiplying by the conjugate can sometimes really help you out. Because all this messy stuff with the square roots, it cancels each other out. And finally I have last, which is negative 10 times 10, which is minus 100. So you have that. And on the bottom you have x squared over x squared plus 100 and then plus 10 right there. And now you can see I'm going to just use my eraser to do some simplification. Those hundreds go away. And now that the hundreds go away, I have an x squared over an x squared. Those two numbers will always be the same. We're coming in towards 0, but we're never actually hitting 0. We're just approaching 0. So this can divide out with this one. And I'm left with a 1 right there. And now as we approach 0, what happens? The top is 1. This is going to be going to 0. So I'm going to get the square root of 100, which is 10, plus another 10 is 1/20. Really a nice problem. It's the kind of thing you'd never be able to guess at the answer to this without doing the analysis and figuring it out. If you want to graph this thing using Decimus, you can, and if you let x go to 0, you'll see that the value of the function approaches 1/20. So there's a good example of how we can actually evaluate functions to find the value of the limits. And next time, as I say, we're going to do trig functions.